So hello everyone, good evening to one and all. So I'm myself Sagar JC. I'm one of the core members of Nakshatra Sciences. So today we'll be having a student seminar by our students of Winter School in Space Probe Observational Astronomy program. So today we have Group 3 of the uh, batch who will be presenting on solar physics. So yeah, Group 3, can you start presenting from now?
Hello, am I audible?
Yes, you're audible, Aryan.
And I think my screen is also visible, right?
Yes.
Yes. So, hello
So from
everyone.
group three, when you're presenting, give you a small introduction of where you're from and your interests, and then you can
Right,
begin.
right, right. We'll do it in the beginning only, right?
Yeah, fine.
Okay, cool. So, hello everyone. We are students from the Observational Astrophysics Winter School program by Nakshatra, as Sagar told. And I am Aryan Shejal. I am a physics graduate from Ferguson College. And currently, it is my gap year where I'm exploring other fields of physics, specifically astrophysics, and seeing what I really like, and also gaining skills along the way. My research interests include stellar astrophysics and, well, a new found interest, X-ray astronomy, that I've like got a chance to explore in this particular program itself. And yes, thank you. Next, Debadrita.
Hello, am I audible?
Yes, you're audible.
Okay, so good evening, everyone. Myself Debadrita Nath, and I'm a second year mechanical engineering undergrad. I'm studying in NIT Agartala recently, and particularly I have had a very keen interest and source of amazement in physics, and particularly in the field of astrophysics. So, in future, I would like to pursue that field more deeply. As of now, I am pursuing mechanical engineering, but along with that, I am also exploring the field of astrophysics as my interest, and I would also like to explore it more in the coming days. Thank you.
Hello everyone. Am I audible?
Yes, you're audible.
Okay. Hi, I'm Madhushri Ravichandran and I completed BSc Physics in Kongnada Arts and Science College, and now I'm in like 1.5 year gap to do my like either masters or PhD in astrophysics, and my research interest in dark matter and dark energy. And also, I would like to explore more in astrophysics and all. Thank you.
Hello everyone. Am I audible?
Yes, you're audible, Tom.
Okay, my name is Tom Raj Daniel and I'm from Kerala. I have just completed my postgraduate studies in physics from Alamein College, Edattala, Ernakulam. Uh, my research include astrophysics and particle physics. That's all. Thank you.
Hello, am I audible?
Yes, you're audible.
Yeah, my name is Adi. I'm currently doing my integrated MSc Physics first year at Amrita Vishwavidyapeetham Kollam campus. So I'm interested to explore more about astrophysics and hope to learn more about it.
Said.
Yeah. Hi guys, this is Siddharth, and I am studying aerospace engineering from Hindustan University, which is located in Tamil Nadu, Chennai. So my research interest is about exploring the star formation and stellar evolution. So that's it. So in my future, I'm gonna pursue masters in astrophysics, and I proceed to the next.
Hi, I am SK, that is short form, Sukhvinder Kaur Solan. I am currently a PhD scholar and working on AGNs, but my interest is also in solar physics. So, looking forward for a great future ahead.
Hello guys, my name is Naman Tambal and I am a third year undergrad student studying in Himachal Pradesh University. My research interest lies in the area of semiconductor physics, quantum photonics, and astrophysics.
Hello everyone, I'm Jeho. I'm currently pursuing Masters in Ladito College, Madurai, and my beloved field of area is astrophysics. In future, I want to pursue MTech in ECE.
Okay, so I think Sagar, can we begin the presentation?
Yes, Aryan. All the best,
Yes,
everyone.
thank you. So now I would like, this is basically a presentation by the 9 of us, and the aim of this presentation is to give the audience a general overview of what subfields, if not all subfields, if what major subfields exist in solar physics. Starting with the introduction, I would like to hand it over to Debadrita, and Debadrita, can you please begin with the introduction?
Yeah, sure. So starting off with the introduction, the things that we are going to learn and ponder upon today in this presentation are solar flares, prominences and CMEs, solar surface, sunspots and their migration, solar cycle, neutrinos, and lastly, all the solar telescopes and the recent solar mission undertaken by ISRO, that is the Aditya L1. Next slide. So, briefly introducing to solar physics, like what is solar physics and sun in general? Since our high school days, we all have been coming with this general definition of sun, that sun is a constant source of heat and energy to the earth as well as other planets, and it supports the life system. But if I speak in a very scientific way and specific way, like the sun is an ordinary yellow dwarf star of the spectral type G25 in the Milky Way galaxy. Now, what are yellow dwarf stars? Yellow dwarf stars are the medium sized stars that belong to the spectral type G and weighs around zero point 0.7 to 1 times the solar masses. Almost 10% stars in the Milky Way galaxy belong to this category only. They are neither very big or they are neither small. The sun specifically is of the spectral type G25. Here, G2 means that it is comparatively warmer and brighter than average with a yellow white color. We can easily see that the effective temperature of the sun is 5785 Kelvin also. The sun was born about 4.6 into 10 to the power 9 years ago, and currently its mass is about 330,000 times that of the earth. There is a fun fact about sun, like the equatorial rotation period and the polar rotation period, it varies, and this variation is due to the differential rotation. Now, if I say like how the sun was born, as we know that the sun is a star, every star is born from nebula. So the sun was also born in a similar way from the solar nebula. It was born from contracting interstellar gases that started spinning about 5 billion years ago. And when the core temperature became large enough, the fusion process started and hydrogen fused into helium, and then the birth of the sun took place. While studying about any particular star, the question that comes to our mind is like, what is the ultimate fate of this star? Similar is the case with sun also. The sun is now about halfway through its 10 billion years journey, and since it is a yellow dwarf star, most of the yellow dwarf stars become red giants at the end of their life, and they ultimately turn into white dwarfs. At that time, during the red giant phase, the center of the star contracts and the outer layers swell, becomes reddish in color and cool down. And then at the end, it gets rid of the outer layer and contracts to a white dwarf. So this is what is the ultimate fate of the sun is going to be. Next slide. Speaking in a historical timeline, from when did people start to study the sun? The study of solar physics and sun began very long ago, as much as we can date back to before 600 BC. But in a proper way, it began from Nicholas Copernicus, because before that, people believed like the sun rotates around the earth. But Nicholas Copernicus was the first to suggest that no, all the planets, including the earth, rotates around the sun and it is the center of our galaxy. So this model that suggested by him was known as a heliocentric model. His work was further expanded by Kepler and Galileo was the one to make the first telescope and he observed the sunspots. Day by day, the solar physics also got developed. And when we come to the modern solar physics, it focuses on understanding the photosphere, coronal heat problems, sunspots, etc., and a lot of other stuffs. Next slide. So the first question that should come to our mind while studying the solar physics is, why should one even study the sun? The solar physics is not an independent branch of study. It intersects with many other disciplines of astrophysics as well as computer science. It will help us to know more about various phenomena like the stellar evolution or other branches like plasma physics, particle physics, as well as a very technical part known as the computational physics. So, when we know about this, it will also help us to know more about the other interdisciplinary fields, and it will help us to work in those fields also in a very collaborative way. Secondly, the solar eclipse has been a constant source of awe and wonder to us since ages. It was actually first time when Einstein's general theory of relativity got confirmed. It was only because of the solar eclipse, and solar eclipse also help us to understand the corona of the sun. This is the reason why we study the solar eclipse, and it has been a constant source of study in the field of solar physics. The sun also has a profound impact on climate and space weather on Earth, and it provides energy and warmth. And in future also, sun can be a very great non-conventional energy source when the conventional energy sources dies off. Now, the most basic thing is that the sun is our nearest star, and it is very easy for us to understand the sun in a better way rather than the other stars that are very far away from us. And studying the sun will help us to know more about the stellar processes that goes on in our universe, like the stellar evolution, the stellar formation, how a star forms, the stages of the star formation. All these things can be understood when we study the solar physics and particularly sun in general. So with this, I would like to hand over the presentation to the next person, that is Sid. Thank you.
So hi guys, this is Sid. So today I'm going to talk about solar surfaces. So why is it necessary to study solar surface? So by observing the solar surface, we can know about the dynamics of the sun, and we can predict the future of the sun, which we're gonna see later in this session. So next, yeah, first we want to see about the structure of the sun. So in sun, the nuclear fusion takes place in the core of the sun. So here, helium is produced by the nuclear fusion of to hydrogen, and lot of energies is released in the nuclear fusion. So this energy is transferred to the outer layer of the core, known as the radiative zone. So in this radiative zone, the energy released from the core of the star is transferred to the outer layer and known as convective zone. In this around in a convection currents, and this energy is transferred to the another outer layer known as the photosphere. So we're going to see later in this photosphere what is it. And above the photosphere, there is something called as chromosphere, which is the thin layer of sun, which contains the ionized gases of helium and hydrogen, etc. So these are the pathways in which the energy transfer occurs in the sun. And next. So first we're going to see about photosphere. So it is the outermost layer of our sun, which we can see through the telescope. Every images we see of the sun is the image of the photosphere. So this photosphere will give rise to the solar flare and sunspots and solar granules, etc. So which we're going to see later in this. And this sunlight produces a continuous spectrum of light, but it some elements observe this continuous spectrum and produces some dark lines in the spectrum of the light, known as conifer lines, which we can observe through the telescope. So by this, we can study the composition of the sun. And next. So So solar granules. Solar granules is formed in the surface of the photosphere. So this happens because of the temperature difference in the photosphere. So the hot plasma inside the convective zone is transferred to the surface of it, and it gets cooled afterwards. So it expands and goes inside. And as it cooled, it gets denser. So this process continues in a cycle to form expansion and contraction that you can see in the left of the image. This is how the solar granules forms. So they have a lifespan of 8 to 20 minutes. So next. So the solar blast, which is ejected from the surface of the sun, forms some magnetic field of the sun known as the heliosphere, which protects us from the cosmic rays from the outside galactic cosmos. And you can see here in the left. So in the right, you can see the surface of the sun and the photosphere, how it evolves and how the dynamics involved. You can see it. So by this, I conclude and pass it to the next person. Yeah.
Hello everyone. Am I audible?
Yes, you're audible.
Okay. Now we are going to talk about sunspot and their latitudinal migration. So first, what is actually sunspot? Sunspot is a dark, cooler, larger region on the solar photosphere where magnetic flux is concentrated. So when you look at an image of sun, that is of the photosphere, you can see large sunspot, small spot, and even sunspot groupings in the sun. It is a darker region on the surface of sun, and they are dark because they are cooler than the surrounding surface, but they are still incredibly hot, about 3,800 Kelvin temperature. And we know that luminosity is proportional to 4th power of temperature, and it comes from Stephen Boltzmann law. And when we look at something cooler against a background of much brighter, they are going to look dark, and that's why it look like dark. So they're not a really dark area, but just cooler region of the surface. A large chunk of sunspot would be seen with the naked eye, although it is very dangerous to look at the sun directly because it can damage your eyes. And actually, the earliest recording of sunspot are from China over 2000 years ago, and the first European he was observed is Galileo. Next slide. So there is a question arise: are sunspot magnetic phenomena? So first we can observe or study the magnetic properties of sunspot through the spectral lines from the sun. So a spectrum means it is a range of colors or wavelength of electromagnetic radiation. And we know that when a light is passed through a prism, it is split into 7 colors. So a light contains the 7 colors, and it's called a spectrum. So and we know that the splitting of spectral lines in strong magnetic field is called the Zeeman effect. So when we take a spectrum of the sun and take our observation in the magnetic field of sunspot, then we can see that the spectral line from sunspot split into 3 lines. And we can see this in the left figure. And we can actually measure the strength of the magnetic field because the amount of splitting also depends how strong the magnetic field is. So now that's not the only way we can look at the sunspot. We can also look at some of the magnetic loops we get. We can see a little loop-like structure in the image, which looks like our Earth's magnetic field. But here, the magnetic field lines are invisible in our Earth. That is, we can't see them. But in sun, the plasma follows those lines, and it allows us to see them and how they connect sunspot together. So magnetic field governs most of the solar activity we can observe, but how they do this is still poorly understood. Next slide. Now let's look at sunspot migration. The location of the sunspot on the sun is changes and it is called migration of sunspot. And this is seen in what we call the Monter butterfly diagram. The figure is given below, and the figure showing where the sunspot appears during each cycle. So if you observe a cycle, at the beginning of the cycle, they form at more northerly latitude, and at the end of the cycle, they form more closer to the equator. That is, sunspot migrate from both sides of the solar northern and southern hemisphere to the equator. So we get this pattern. We get this pattern when we map out where the sunspot occur each time. So very early in the cycle, they are very high, that is about 30-degree latitudes, and very late in the cycle, they are much closer to the equator, giving us a distinct pattern that we see each time, and giving the impression of butterfly in a line, and they are giving its name butterfly diagram. So actually, the latitudinal movement of the sunspot is called migration of sunspot. And next slide. So now we look how the sunspot is formed. What we see is that the sun's magnetic field, we said that was the underlying cause of all the activity, is formed by what we call the solar dynamo and differential rotation. And the solar dynamo means the gas underneath the sun, which generate electric current, which when rotating forms a magnetic field. So now, typically a magnetic field looks something like that in the first one in the left diagram, left figure. The magnetic field lines just form a big loops and something like this in the air. That is exactly what happens. And in air, Earth is a solid sphere, so it is rotating together. But remember that the sun rotates differentially, and what that means is that it's spinning faster at equator. So over time, the area of the magnetic field lines near the equator moving faster. Those near the poles are moving slower, and the equator will lap the poles because of this differential rotation. So the equator of the sun rotates much faster, and it takes 25 days for a complete rotation, but the poles takes 36 days. Because of that, the magnetic field that are inside the sun get twisted up, and after number of rotation, we can see that instead of having the field lines go straight across, they go like in the second and third figure in the left. So because of this, what happens is that the magnetic field lines get all twisted up, and sometimes they start popping out of the surface of the sun, and wherever the magnetic field lines come pop out and goes back into the surface, at those locations, that's where sunspot begin to occur. And when these magnetic field lines burst through, they will slow down the energy transport or decrease it. Cooling of these areas of the photosphere gives rise to the sunspot. So, in summary, sunspots are actually a cool, dark region in the solar photosphere and are caused by the twisting and tangling of the solar magnetic field. So now let's hear from my colleague. Thank you.
Yeah. Good evening, everyone. I'll be talking about the solar cycle. First slide, please. Yeah. So the idea of the cyclic solar cycle was first hypothesized by Christian Horebo. A regular observation during 1761 to 76, he found that the variation in the solar cycle, sunspot cycle, is cyclic. But solar cycle got its identification from the work of Samuel Henry Squabe, who observed sun for 17 years and found variation in the sunspot numbers. To honor him, it is also called Squabe cycle. It is also called sunspot cycle as well as magnetic cycle. A solar cycle lasts for around 11 years on an average, but this period varies from between 8 to 14 years. The sun goes through a period of maxima and minima in the cycle, and it's during the peak of the maxima that we notice the maximum number of sunspots of that cycle. They varies from 100 to 150 spots at the peak, depending upon the strength of the cycle. So a stronger cycle has more number of sunspot at its peak, and a weaker cycle has a less number of sunspots at its peak. It is during the maximum that the sun's magnetic field too flips. So it is also called the magnetic cycle. Now, it moves in the next in the consecutive cycle during the peak. Once again, the solar magnetic field flips and it regains its original phase. So this 2 cycle, that is 22-year cycle, is also called Halley cycle. Now this 22-year cycle forms the magnetic cycle of the sun. So the image shows on the top that the solar surface from period of 2010 to 2020 in extreme UVs. It is actually depicting one full solar cycle. As we see, the activity on the surface peaks slowly, and then in 2014, it is maximum. And as the cycle progresses, the solar activities further slows down, and when it reach around 2019, we see there is no activity seen on the surface of the sun. Actually, this maxima period lasts for about from 4 to 4.5 years to 6.5 years, and varies in that period. And 2014 is the peak of this solar cycle. And the image below is depicting the 400 year of solar spot observation. Now here each peak depict the each peak is solar maximum, and you see how there is a modulation in the peak. It is not constant. Each consecutive cycles, solar cycles, are not similar. So in a general trend is that a strong solar cycle is followed by a weaker one, and vice versa. But it is not always true in the cycle. As you can see, not always the stronger is always weaker one, but sometimes they alternate may happens. Now solar cycle from 1642, it is excuse me. Now from 1640, as you see in the left hand side of this bottom image, 1640 to 1710, there are no records of sunspot. So this period is called Maunder minimum. So during this period, we had mini ice age on Earth. So the sunspot cycle has severe effect on the climate of Earth. It is a during solar cycle, the CMEs to occur, and the effect of CME is extended. Now, I would like you to please change the slide. Yeah. So during the solar cycle, we see the CMEs and prominences and sunspots. So here the sunspot is may seems a small spot on the surface of the sun, but it's not actually. It is as large enough to engulf the entire Earth. Sometimes the sunspots are so big that it may engulf more than tens of hundreds of Earth and inside it. So and this sunspots at the beginning of the solar cycle, they usually appears at the latitude around 30 to 45 degree north and south of equator. But as the cycle progresses, they are more and more prominent at the lower latitudes, and around at the end of the cycle, they just are around 10 to 15 degree of the solar north and south of the equator. And not only this, these leading sunspot as well and the following trailing sunspot, they have opposite polarity in both the north and south hemisphere. To give an example, if the leading polarity in the northern hemisphere has a north pole, then the trailing one will have south pole, and in the southern hemisphere it will be opposite. The leading will have south pole and the trailing will have north pole. So, and it and in the next consecutive cycle, it varies. Like if in the first cycle it is leading as North Pole in the northern hemisphere, in the next cycle it will be south in the northern hemisphere, and consecutively opposite in the southern hemisphere. And besides, they also these sunspots also are inclined. The leading one is inclined to the trailing one at an angle, and this angle increases with latitude. So this is also called Halley's cycle. Now, as you see in the during solar minimum, there is little or no sunspot visible. Next slide, please. Yeah. So now these CMEs are very common during the solar maximum. As the sun goes from maximum to minimum in its cycle, we see the effect of these flaring activities, solar sunspots and CMEs increase with the peak, and and these CMEs, they have severe effects on the Earth's climate. Like now we are currently going through 25th solar cycle, and we are in the maximum phase, and it will peak around January 24th, between January 24th to January 2024 to October 2024, anywhere in between. So we do see a lot of activities happening on Earth because of these. On December 3rd this year, we had a huge corona hole facing Earth, from which rest with this solar particles, high-speed winds, were directly facing Earth, and they reached Earth on 5th of December. That is 36 hours after they were originated. Now, and we had a severe geomagnetic storm on Earth, which has severe effects on Earth. So, thanks to our magnetic field, which protect us against this harmful cosmic rays, but otherwise we would be reduced to like Mercury, which is showing as a comet-like sodium tail, because of these cosmic rays hitting its surface constantly and producing that sodium tail. And we see we can observe Mercury sodium tail like a comet, like we see in a comet, because of this extreme cosmic rays effect. So next slide, please. Yeah. So how it may seem that this solar cycle, these activities are so harmful and extreme, but we perceive on Earth as a beautiful auroras at our poles, and not only on Earth, we do see them on other planets like Jupiter, Saturn. We do see these polar lights there too. But these are the cosmic rays coming from the sun and reacting with our solar atmosphere and creating this beautiful sheen of light. And they are wonderful sight to see. And it may sound that the sun solar cycle is are too harmful for Earth's weather condition. Men and women. Yeah. Sorry.
I think someone accidentally muted. You can continue.
Sorry. Okay. So we see this beautiful sheen of lights, and we may say that the solar cycle is very harsh, but it as we have seen that absence of solar cycle led to extreme weathers on Earth, like ice age and all. They are needed, and we should be thankful this happening on on our star. And these type of solar cycles are like stellar cycles are seen in other stars too, and been studied, and they usually happens in the middle-aged stars. And now I think I'm over time. I will stop here for my colleague to continue. Thank you.
Hello, everyone. Hello, am I audible?
Yes, you're audible.
Okay, so I'll be explaining about solar flares. Okay, next slide, please. Okay, so like before knowing about solar flare, we must know what is a solar flare. Like, so a solar flare is a sudden intense burst of energy on the surface. So as like everyone know, our star is a celestial body which undergoes the process of nuclear fusion. So in which it combines the hydrogen and creates helium atom, right? So in that process, it creates a lot of charged particles. So charged particles is the reason we have the flow of electric current. So which in turn it produces the magnetic field. So like when the sun it builds up magnetic field for a long period of time and it suddenly releases it, it comes in the form of solar flare. So when the solar flare releases its energy, it actually comes across in the entire electromagnetic spectrum, ranges from X-rays, gamma rays till radio rays, and also sometimes it ejects some of its material into the space. So to speak about its speed, this solar flare actually travels at different speeds as it is accompanied with some material and some energy. But to be said an average, it will be around 300 to 800 kilometer per second. And usually the solar flare happens near a sunspot, and the energy produced during the solar flare is 10 million times like energy produced during a volcano. So like think about it, it's a really a lot of energy. This is also a reason like why we are studying about the solar flare, because we have been developing our technology for a very long period of time, but like because of this one solar flare, we could destroy everything in our earth. Okay. Next slide, please. So the solar flare actually classified into different categories based on its strength and the X-rays it emits. By like the table that's been given here at the bottom, we can see the B class solar flare is the smallest one, and the X class solar flare is the vigorous and highest one. So it actually produces energy in the form of watt per meter square. And the B class, it produces very less than or equal to 10 power minus 6 watts, and whereas this X one creates like greater than or equal to 10 power minus 4. And this categorized and developed by GHOST, which is stated as geostationary operational environmental satellites. This satellites actually detects the amount of X-rays which is being sent, which is being emitted by this each classes of solar flares. Yes, and like usually in our Earth, we'll represent each of the Earth parts using some colors, like to represent the thermal radiation. Likewise, here also the different classes of solar flares has been represented in different colors in this graph. So if you can see, B is like it's around green color, as it is like it's a very small solar flare, and X is in a red color region, as it is a high like vigorous solar flare. And each solar flare classes has scale from 1 to 9. So if you take X, even it's like a very high and vigorous solar flare, it can range from like X1 to X9. And yeah, and also this M class solar flare, right? So X is the highest one and B is the lowest one, whereas M is considered as the moderate one. The M, like because of this M class, it could not impact Earth so much, but it could sometimes cause some effects to the astronauts in space. The next slide, please. And the impact on Earth and causes. The first one is geomagnetic storms. It's because of this solar flares, it emits a loss of energy and particles in the space, right? Like when these particles reaches Earth, it actually creates the geomagnetic storms, which is like contraction or distortion of the magnetic field around Earth. So this actually comes under the non-visible range. When it comes to the visible range, the charged particles in the solar flare actually like mixes up with the ionized particles in our atmosphere and creates this beautiful aurora, like we can see it in our higher altitude places. And the next one is radio communication disruption. We everyone is using radio as a medium for communication, and radio uses our atmosphere as a medium to propagate, right? So whenever we have solar flare, it actually mixes with our atmosphere and it changes the ionization phase of our atmosphere. So when its ionization phase changes, radio waves is also got disturbs, like because it considering our atmosphere as a like medium of propagation, right? That's why it disturbs the radio communication and satellite operation. We have a lot of satellites in our space, right? Whenever the solar flare happens, it actually affects the satellite, and some satellites are using this radio waves as a medium to communicate with ground telescopes and other things and all. So this causes the satellite operation and all. And power grid instabilities. Whenever we have the solar flares, it actually creates one current in our atmosphere that is called geomagnetically induced current. So when this current when it comes in our atmosphere, it actually overloads our transformers and it heats up our transformers. Due to this, we can have some blackouts and power cuts in some places. Yeah. So next slide. So this is today's news of solar flare. Recently, our sun had a huge burst, and this is not today's news. This been happening from December 14 until now. And this solar flare is considered as the more biggest one since 2017. In 2017 also we had one this bigger solar flare, and it already caused some blackouts in some areas. And after this is the bigger solar flare, and this is considered as the most powerful one in this present 25th solar cycle. And also this is not the most active region of the sun. It will attain its peak in the upcoming June and 2025. And the experts are also saying at that time also we'll be having a big solar flare than this one. And also they are asked us to they are asked us to take some precaution steps to prevent that. And thank you. That's it.
Hello everyone. Am I audible?
Yes, Adi, you're audible.
Yeah. Hello everyone. This is Adi. I'm going to speak about coronal mass ejection, also called as CME. It is a large explosion of plasma and magnetic field from the sun's corona. It ejects billions of tons of coronal materials, and its speeds range from 250 km per second to 3000 km per second. The time period to be estimated is to reach the Earth is 15 to 18 hours. Next slide. As we see in this figure, the more explosive CMEs generally begin with highly twisted magnetic field structures called as flux ropes contained in the sun's corona, becomes too stretched and realigns into a less tense configuration, a process called as magnetic reconnection. This can result in the sudden release of electromagnetic energy in the form of solar flare, which typically accompanies the explosive acceleration of plasma away from the sun. This is what CME is. These type of CME usually take place from areas of the sun which localized field of strong and stretched magnetic flux, such as active region associated with the sunspots. Next slide. As we see in this video, the size, direction and speed are the important parameters. This is being captured by the stereo satellites to study the three-dimensional structures of these corona. The instruments can range from 1.5 to 32 solar radii. Next slide. Solar prominence. It is also called as filaments. It is a large bright feature extending outwards from the sun's surface. It anchors to the sun's surface in the photosphere and extends outwards in the sun's hotter outer atmosphere called the corona. It forms over a timescale of about few days, and stable prominence may persist in the corona for several months, looping hundreds and thousands of miles into the space. Next slide. The video shows the red glowing looped material called the plasma, a hot gas compressed of electrically charged helium and hydrogen. The prominent plasma flows along a tangled and twisted structure of magnetic field generated by Sun's internal dynamo. An erupting prominence occur when such a structure becomes unstable and bursts outwards, increasing the plasma. By this, I conclude and pass it to the next person.
So now we will be talking about solar neutrinos. Next slide. What are solar neutrino? The solar neutrinos are elementary particles which are electrical neutral and extreme lightweight. They interact only through weak nuclear force and gravitational field. Solar neutrino don't interact with the electromagnetic forces. That is why most of them pass through the ordinary matter without any interactions. So why are solar neutrinos important to us and why should we care about them? As we know that solar neutrinos are formed in the sun cores during nuclear fusion in which two protons combine to form a helium atom and the neutrinos are the byproduct of this reaction. So solar neutrinos are crucial to study so we can get to know more about the inner working of the sun and provide a unique window into the nuclear reaction that powers the sun. Now let us discuss about a very important experiment, the Homestake experiment and the solar neutrino problem. Next slide. The Homestake experiment was the first experiment to detect solar neutrino, which was built in Homestake gold mine in South Dakota. The experiment was headed by two astrophysicists, Raymond Davis and John N. Bacall. This experiment used 100K gallons of dry cleaning fluid named perchloroethylene to search for the neutrinos. David's scientific partner, John Bacall, had predicted how many neutrinos should arrive from the sun and transform one of the chlorine atom in the detector into the another argon atom. But the experimental resulted only one-third of the neutrinos seemed to arrive the detector and two-thirds of them were missing. This historical disagreement between the predicted and observed flux of solar neutrino is referred to as the solar neutrino problem. So, what things led to this disagreement and where were those two-thirds solar neutrino missing? Was there something wrong with the David experiments, Becquerel's calculation, or the current model of the sun, or was it in the picture of neutrino? So the solution to the solar neutrino problem was the neutrinos oscillations. Next slide. Neutrino oscillations was first predicted by the Bruno Pontecorvo in the year 1957. As we know that neutrino exists in three flavors. First is the electron neutrino, second is the tau neutrino, and the third is the muon neutrino. So the neutron flavor oscillation refers when one neutron changes into another neutron. The electron neutrino, which is produced in the sun's core, can change into muon or tau neutrino through flavor oscillation during their journey to Earth. The Super K experiment and the SN observatory confirmed the neutrino oscillations in the late 20th and the earlier 21st century. So the missing two-third of the solar missing of the two-third electron neutrino were being changed flavor from one flavor to another in the form of tau neutrino and muon neutrino. The leaders of these two projects received the Nobel Prize in the year 2015 for their significant contribution to the discovery of the neutrino oscillations. Next slide. Here we can see an image of neutrinos directly emitted from the core of Sun obtained by Super K Neutrino Telescope located in Japan. Now I would like Jeho to present the next slides.
So let's get into solar telescopes and Aditya L1. Next slide, please. People tend to be curious about the things they don't know. Likewise, we wanted to know about our sun, like why our sun is in this color, why is it hot, and why is it called a star. If we know something, if we need to know something, we need equipments. So the equipment that used to study and observe the sun are called as solar telescopes. We know that study of sun is called as heliophysics. Like solar telescopes are also called as heliographs. There are many solar observatories. Some examples are Udaipur Solar Observatory, Kodaikanal Solar Observatory, and Me Solar Observatory. In Udaipur Solar Observatory, their mission is to observe the weather conditions, solar winds, and solar flares. In Kodaikanal Solar Observatory, their objective is completely about the sunspots. They give the details of sun about 30 years. In Me Solar Observatory, it's actually in Hawaii. Their main goal is to study the sunspots and solar winds and CMEs. Next slide, please. There are many types of solar telescopes, a few of them. Actually, we differentiate the telescopes by their wavelengths. So for the optical telescopes, it will be like filters will be having wavelengths in the visible spectrum. Example, H alpha telescopes and calcium potassium telescopes. These come under optical telescopes. For the space-based telescopes, if we place a telescope in Earth, we have Rayleigh scattering, reflection, absorption, etc. Simply too much disturbances. So the advantage was if place it in space, we can get effective details. Radio telescopes. So it will be used to analyze the solar flares and the coronal mass ejections. Space weather telescopes. It will be used to analyze the weather condition by studying the sun. Coronagraphy is, let's say, like during solar eclipse, we know the moon covers the sun. At that time, if you place a camera or anything to record, that will be act like a chronograph. What actually means is when moon covers the sun, the photosphere in the sun will become invisible. So the visible regions are only chromospheres and the corona. So that's why it is called as coronography. Next slide, please. Okay, now we talk about Aditya L1. That is, Aditya means sun and L1 is Lagrangian point 1. People ask whether Aditya L1 is a satellite or a spacecraft. Actually, it is a coronagraphy spacecraft. So, the objective of Aditya L1 is to study about the coronal region because the temperature difference from the chromosphere to corona is about million Kelvin. We need to know the reason for it. And also, the main objective is to study and find out the reason for the coronal mass ejections and the solar flares. So the payload contains visible emission line coronagraph to study the outer solar corona and ultraviolet imaging telescope to capture images in the ultraviolet range. So Aditya L1 recently took the images of the sun in the UV range. The launch vehicle was PSLV C57, launched from Satish Dhawan Space Center, and we have an international collaboration with NASA too. Next slide, please. So why they place Aditya in L1? So basically, there are 5 Lagrangian points. If we place in L2 point, then there is nothing to do with our objective because our objective is to study about sun. So if we need to study about the extraterrestrial bodies, then the L2 point is best. And if placed in L3, it is behind the sun. So it is not good for communication. And what if L4 and L5, they are Trojan points and they also much further from the Earth than L1. So L1 is best for our objectives. That is why it is Aditya L1. Thank you. Over to the next person.
Hello everyone. So we have arrived at the end of the presentation, and now to summarize everything that we have learned so far. Starting with the first topic, the solar surface. Basically, the solar surface is called the photosphere, and just above the photosphere, there is a thin atmosphere which is called the chromosphere. The extended atmosphere of the sun, also called as the corona, is basically called the corona because it looks like a crown. And the coronal heating problem, which we briefly discussed in the previous few presentations, is the temperature of the solar corona is extremely high. The temperature ranges in millions of kelvins, and the challenge here is that we don't really know, or we don't have a good explanation as to why this is happening. And this is an active area of research. Next topic was sunspots and their migrations. Now, sunspots are dark spots on the surface of the sun, and these are characterized as the regions of high magnetic activity. These have also been observed to move towards the equator over the time, and this is basically what sunspot migration is all about. If you visualize this on a graph, this is what we call the Maunder butterfly graph, because the plots basically trace the shape of a butterfly, and that is exactly why it is called the butterfly diagram. The next topic which we saw was the solar cycle. The solar cycle is an oscillatory 11-year cycle where the solar activity goes under an increase and decrease. This happens every 11 years, and the reason why we study this is because solar activity is directly affecting climate on Earth, telecommunication, and others things as well, like geomagnetic storms. So studying the solar cycle gives a good hand over predictability of such events, and this basically we have a good idea of how exactly this will affect our Earth's atmosphere and telecommunication devices, which directly relates this to common people. Another topic which we explored today was solar flares. Solar flares are basically release of energy from the sun in the form of photons and high energy photons. Basically, this happens when a magnetic field line snaps and releases an extremely high amount of energy, and this energy is received on the Earth in the form of X-rays and gamma rays. The classification of X-ray solar flares is done with the conventions ABMX, and the frequency of the flare increase as the sun approaches its solar maxima. This is quite obvious because we have seen that during the solar maxima, the magnetic field activity of the sun is extremely high. The next topic that we explored was CMEs and prominences. CMEs, meaning coronal mass ejections, are basically stellar winds and that carry magnetic field and that come towards the Earth. Coronal mass ejection are basically consisting of charged particles, thus they scatter off radio waves, and this can cause problems in satellite communication. And this is one reason why, this is one big reason why studying CMEs is important, because satellite communication is one of the very crucial parts of our lives now. And another thing is CMEs also affect space weather. So for potential future space space projects, having a good knowledge of having a good insight on what CMEs do and how CMEs affect the space weather is extremely important. Prominences are loop-shaped projections on the solar surface, and basically prominences are the tracers of magnetic field lines. They typically have a life of a few weeks, but some of them can even survive for up to months. Both these coronal mass ejections and prominences are a manifestation of the sun's magnetic activity. And this is an indirect way of studying, or you can even say a direct way of studying the sun's magnetic activity. Next topic that we explored today was solar neutrinos. Solar neutrinos are neutrinos that are produced in the stellar core of our sun, and because they are practically inert, they only interact via the weak nuclear force. The gravitational force is actually quite negligible for such a small mass. That is why the only way they can interact with any other atom, molecule, whatever, is through the weak nuclear force. And this is basically the challenge in detecting the neutrinos. And studying solar neutrinos is like a way of probing into the interior of the sun, which is not possible from different like telescopes or even like spacecraft, because you can't really like tell what is happening inside the core of the sun, right? But neutrinos is one way of probing into of what might be happening inside the sun. This is also valuable in terms of understanding stellar astrophysics, as well as the particle physics of neutrinos. The last topic that we saw for today was solar telescopes and Aditya L1. Solar telescopes basically are designed according to the requirement, and the requirement can the requirement is basically what the purpose of that particular observation is. For example, there are H alpha solar telescopes. H alpha solar telescopes basically observe only the H alpha line of the hydrogen spectrum. This is to get a very specific idea about this particular line. Another telescope is the white light telescopes, which offers a broad waveband study. But as you guys might have guessed, with a broad waveband, we lose information on the resolution that we are observing. Other telescopes are UV and X-ray telescopes, and because X-ray and UVs cannot really penetrate the atmosphere of the sun, these telescopes are generally, these payloads and instruments are basically present in space on space-based observatories. And another telescopes are radio telescopes. So radio telescopes basically help us in predicting solar flares, because before there is a solar flare, there is a acceleration of electrons, and these accelerating electrons give out radio waves, and these radio waves come to us, and this is like one way of potentially predicting a solar flare that could like whether or not it can affect like the Earth's atmosphere or not. The Aditya L1 project is ISRO's coronary spacecraft, and its objective is to study the sun. That is why it is also named Aditya L1. And L1 because it is going to be present at the Lagrange 1 point, and it will reach Lagrange 1 point on the 7th of January 2024, which is about 2 to 3 weeks from now. And it has 7 different payloads to undertake different kinds of tasks. For example, some payloads are to specifically study the chromosphere, some are to study the particle background, and also the corona. And that concludes today's presentation. Thank you very much. Thank you very much for patiently listening to us. It has been about an hour. And if you guys have any questions, you guys can like either unmute or drop those questions in the chat box. Thank you.
Thank you, Aryan, and thank you, Group 3. Great job, everyone. The presentation was very good, and keep up the great work, guys. So you all were able to convey us all the major fields of solar physics in such a short and brief way. That's very good. And yeah, I look forward to seeing more of your work in the future, guys. Good work, good work. So yeah, in the meantime, does anyone have any doubts or any questions? If you want to ask our students, you can put it in the chat box or unmute.
Yeah, I do have a doubt.
Yeah, Vignesh.
Yeah, so in the PPT, like when you were describing the different layers of the sun, yeah, in the radiator zone, it's written more, the energy, it takes more than 170,000 years to radiate through.
Yeah.
How do you get that like that correct time, and why so?
That is just an approximation, and it's not accurate because there is a term called a random like free motion path of a photon. So this is basically nothing but the photons which is produced in the core of the sun goes to the outer layer of the sun. So in which it will interact with the other particles, like it will bump into the other particles and go reflects back like an inelastic collision likewise. So this happens multiple times just to come out from the photon from that layer to the outside layer. So it takes a huge amount of time. It takes from a day to like millions of years to get the photon from inside to the outside of the sun. So due to the inelastic collision happening inside. So that's a very long time there.
Thank you.
Yeah, and moreover, Vignesh, so basically, this is the process which is what is helping the sun to be stable, right? So these photons will collide with the gas molecules or the plasma molecules of hydrogen, helium, all those, and then they impart energy to them, and because of that they move outward, like they expand, like they will help in maintaining hydrostatic equilibrium, isn't it? So in this process, photons will lose some energy and they collide, and the molecules will gain energy and they help in maintaining gravity, like opposing the gravity.
Yeah.
Okay, so any other doubts?
Thank you.
Sharath, you have unmuted. Do you want to ask him anything? Sharath Shivram Nair, hello. Okay. Anybody else? Any doubts or anything? Okay, so if there are no more doubts, you can always reach out to us. You can ask any questions in the Nakshatra discussions or in the Telegram group, where I'll forward the doubts to the students and they can answer. And yeah, thank you everyone for joining this evening. And we'll be having few more seminars and project presentations in the upcoming weeks. So looking for everyone to join again. And yeah, thank you. Bye-bye.
Thank you. Bye.